Do we have the same amount of N on both sides?
Yes.
Do we have the same amount of O?
Yeah.
Do we have the same amount of Cl?
No.
No, because we've got two Cl's on the product side. So to balance this out, what am I going to do? How would I get more Cl over here?
We will have to put a 2 in front of NOCl, but then we will also have to put a 2 in front of NO on the product side.
Perfect. All right, so that's step one for solving, right? So we have a list of steps that we have to follow to solve one of these problems. The first one is write a balanced equation. The next one is write an equilibrium expression. So we need to write an equilibrium expression for this one. So Aiden, what would my equilibrium expression be for this problem?
This is the same one as before.
So what do you mean? What's the equilibrium expression for this? K is equal to what? Yep, products over the reactants, and they're all gases, so all of them will be included. So what are we writing up top? Okay. And also keep in mind it says equilibrium concentration, so we're looking at concentration. So, yep, so square bracket, yep. So we have NO. There's a coefficient of 2, so what are we going to do to the NO? Do we times NO by 2, or do we raise it to the second power? Good. Times Cl. And then that's going to be over our NOCl squared. Okay. So we have our equilibrium expression. So we've done our first two steps. Then it says calculate Q and see which way it's going to shift. So we're going to look at this problem, and it says at 35 degrees, the equilibrium constant is this. So we have our K value. So we know that K is equal to 1.6 times 10 to the negative fifth, right? It tells us our K value. In the experiment where we have 1 mole of NOCl placed in a 2-liter flask, what are the equilibrium concentrations? So what it's saying is we have 1 mole in a 2-liter flask of NOCl, okay? So the only thing we have is NOCl to start with. So which direction is it going to shift if the only thing we have is a reactant? Emily Gustin, which direction is it going to shift? Yep, so if all we have are reactants, it's going to shift towards the product. So we don't have to calculate Q because we already know which direction it's going to be shifting. All right, so after we do that, we're going to do our brand new skill. Whoops, I thought the steps were underneath it. So after we do this, we're going to do our brand new skill of setting up an ice table. Okay. So when we go to do this, we put this along the side. Okay. So I, C, E. We have our balanced equation, which is 2NOCl forming 2NO plus Cl. So the first thing we need to do is fill out our initial line, like what do we have initially? So Connor, what's going to go on my I line? What do I have initially?
What did you say?
Yeah, so what's going to go on my I line? What do I have initially in this problem?
1.6 times 10 to the negative fifth.
So what that is, the 1.6 times 10 to the negative fifth, that is not a starting value. What that is my K value. So this is my equilibrium constant, K. So this is my K value, which is right here. So that's not a starting concentration. What is my starting concentrations? What do I have to begin with of my NaCl, my NO, and my Cl.
Oh, 1 mole.
I have 1 mole in how many liters?
2.
So what I need to put in here, because we're looking at how the concentrations change. So we don't want moles, we want concentration for my initial. So what would my initial concentration be if I got 1 mole in 2 liters? So I have 1 mole in 2 liters.
1/2.
Yes, so that's going to be 0.5. Okay, so what that means is that we have 0.5 molar of NaCl. Okay, what about my NO and my Cl to start with, Connor?
Nothing because it's not there at the start.
Yep, not there at the start, so we're going to put 0 molar for each of these. Okay, so we have our initial starting concentrations for each of those. So then the next thing that we need to do is we need to figure out our change. So thanks, Connor, for your help with that. Emily Krulikowski, what am I going to do for my change line here?
I just got back from doing something. So what was the question?
Yeah, so what is the change line going to be? What do we put in for the change?
Don't you put X?
Yeah, so we're definitely looking at some value X, but remember it also relates to the
Yeah,
coefficient.
so minus 2X for NaCl,
Uh-huh.
plus 2X for NO, and just plus X for Cl2.
Perfect. Okay. So what we have here is because we have this coefficient of 2, it means that change is double, right? So double the change. Double the change. And then because the coefficient here is 1, it's equal to just the change. Okay. And then because we said that our reaction shifting towards the products, we're going to be subtracting from the reactants and we're going to be building products. So that's why our reactants is a minus and our products are a plus. So plus means that we're making them, so we're adding to them, whereas on the reactant side, we're subtracting. Good. So then the last thing we need to do is fill in our at equilibrium line. So Olivia, what am I going to write for my E line?
Okay, for NaCl, you're going to write 0.5 minus 2x.
Yep.
And for NO, 2x, and then Cl, 2x.
Cl is going to be what?
Cl2 is just going to be x.
There you go. Good. Okay. So now we have these equilibrium concentrations, right, of these here. So we've gotten to that step. What's the next thing we need to do? So we've filled out our ice table. So what is our next move once we do that? Lisa, what's the next thing we're going to need to do?
I'm sorry, what?
Yeah, so now we have our equilibrium down here, right? Our equilibrium concentrations. So what are we going to do with that now that we have these equilibrium concentrations? Where do we put them next? So we filled out the ice table. What's the next step that we need to do? We know, but I want to see if Lisa knows first. So what are we going to do with these numbers that we got down here at the bottom of our ice table? Where are we going to put the 2x, the x, and the 0.5 minus 2x?
Oh, we're solving for x.
Yeah, we have to solve for x. So what are we going to do with these numbers? What are we going to plug them into? So you said we have to solve for x. So how are we going to do that? Where are we putting these numbers?
We're putting them with the constant.
Yeah, so we're putting them back into the equilibrium expression. So we're going to take these numbers and we're going to plug them back into this equilibrium expression over here. Okay, so we're going to do that now. So what we're going to end up with is we know our K value is 1.6 times 10 to the negative fifth. We're going to take these values here and we're going to plug them into this equation. So we're going to have then, and this is going to get messy, right? So our value for our NO2 is 2x and we have the square there, so it's going to be 2x squared. So this gets to be a bunch of fun algebra, right? And then CL is x all over, and then we have the quantity 0.5 minus 2x squared. And that's going to be equal to our k value, which is 1.6 times 10 to the negative fifth. At this point, chemistry is over, and now it's algebra class. We've got to be able to simplify. So like all that algebra that you were doing, like why do I have to combine like terms? Why do I have to do the FOIL? Why do I have to do quadratic formula? Here it is, guys. This is the real world example of what we use it for. Like you can't solve this problem unless you get all of that math in your head. So the first thing I'm going to do is I am going to simplify the top. So if I have 2x and I square it, what does it become, guys? So if I take 2x and I square it, what does it become? Ethan, what does it become?
4x to the second.
4x squared, right? So 2 times 2, right? So we have to square the 2 and square the x. So that becomes 4x squared times x. What would it become then, Ethan?
4x to the third.
4x to the third, okay? So we're going to have 4x to the third on top over the quantity 0.5 minus x squared, right? And that still equals our k value of 1.6 times 10 to the negative fifth, okay? Now, if we wanted to simplify this, right, and we were to multiply this out, that would get really messy. We could do it, right? We could take our 0.5 minus, what is that, 2x? Yeah. 2x. And because it's squared, it would be the same thing as this, right? And then we'd have to FOIL, right? The 5 times this, the 5 times that. And we'd have to go here and there. And then we'd have to combine like terms. Does that sound like fun to you? It doesn't to me. So what if I told you there was a way around it that we didn't have to do this? And this is called the assume x is 0 trick. Okay. So let me explain this logic. And those of you who have Mrs. Cohn or have Mrs. Cohn, I used to get huge arguments about, you can't do that, miss. And I'll explain why you can. Okay. What we're going to do is, because our k value is 1.6 times 10 to the negative fifth, right? So 1.6 times 10 to the negative fifth. That is equal to 1, 2, 3, 4, 1, 6, right? That's a pretty tiny number. So if we've got a number like 5 and we add to it 0.000016, right? And you get this number that is 5.000016, and I tell you to round it to 2 significant figures, your answer is going to come out to be 5.0, right? So it doesn't matter that we added that really teeny tiny quantity to my 5. When I ask you to round it to 2 significant figures, we're going to drop that little teeny tiny change off of it. Does that make sense? Okay, so here's the trick. And Ami, I think this is what you were referring to when you asked me, like, where did that number in the bottom go? What you can do is you can assume x is so small that it's 0. Okay. Now, you can't assume this x up here is 0. You can only do it when we have the add or subtract down below here, because what this says is our x value is going to be so tiny that if I take 0.5 and I subtract from it 0.000016, right, it's not going to look like we really changed anything at all. It would become 4.99 whatever, and when we rounded to two significant figures, it would go right back to looking like it was 0.5. Does that make sense? So what we're saying is this value that we're subtracting from it is so small that it's not going to make enough difference once we do all of our rounding, okay? So we're going to be able to assume that x is small. So now if we do that, what this really becomes is 4x cubed over 0.5 squared, which, let's friends admit, is much easier to do than to go and have to FOIL out 0.5 minus 2x times 0.5 minus 2x, right? That's a lot more work. So in scenarios where our k is really small, when we have the subtraction piece only the subtraction part, we can assume that it is small, okay? Does that make sense? Any questions with that? Okay. So now this becomes a lot neater and nicer to do our algebra and our solving. So we've got our 1.6 times 10 to the negative fifth. And so we can multiply this through. So 0.5 squared times 1.6 times 10 to the negative fifth. And we can go through and we would solve. So when you do that, so 0.5 squared is 0.25, right? So we would end up with 0.25 times 1.6 times 10 to the negative fifth is equal to 4x cubed. We divide both sides by 4. And then we would take the cube root of this thing. Remember all that algebra? Like, when are you ever going to take a cube root of something in your life? Here it is, friends. So you take the cube root of both sides, and you'd end up with an x value that was 0.010. Question. What was the question? I'm recording it right now.
Oh wait, never mind. I figured out.
Oh, there was a hand raised, not the comment. Gotcha. The noise is the same if somebody raises their hand or if they ask. You figured it out, Olivia? You don't have a question? Are you sure?
Yeah. I wasn't looking.
Okay, no worries. So once we do that, we now have our x value, which is pretty darn small, 0.010. And so what is the step that we go from here? Because it says, what are the equilibrium concentrations? So now we have the change, right? What x means is change. Like, how much did everything change by? Man, that pen is struggling. That one's a good one. So that is our change. That is not our final answer. We have to figure out what our equilibrium concentrations are. Let me show this. I'm kind of off the screen. So what's our next step? Drew, what's the next thing we're going to do? Oh, we already did that. We got our x. I solved for x and did all that stuff there.
You just gotta plug it in for the equation.
Yeah, so now that I have my x, I can plug it into these numbers here, right? So my final answer, 0.5 minus 2 times 0.01. So at this one, we said that this would be approximately 0.5. We've already assumed that, right? And then here, we would take our 2 times our x value, which is 0.010. And then x right here is just 0.010. So this tells us that our concentration of NaCl is roughly 0.5. It's not that much different. Our concentration of NO is 0.02, and our concentration of Cl is 0.010. Right. Does that make sense to you guys? So the concentration of NOCl is, so squiggly means approximately, so it's not a hard equals. It's less than 0.5, but not by much. And then our concentration of NO was equal to, or was approximately, squiggle line, 0.02, and then Cl approximately 0.01. Molar, molar, molar. Okay, it's a lot of work for one problem, right? It took a long time because I'm talking through it, right? I'm giving you an explanation. I'm waiting for you guys to give me stuff. If you're just cruising along on your own, it's not so bad. But that's the assume x is 0 trick. So Ami, does that explain the question that you asked? Okay.
Sorry, yeah.
Yeah. So if it was an addition situation as well, like, because sometimes you'll get, like, if you have some products here to begin with, you might have like 0.1 plus 2x over here. It would work the same way. It's only for the subtract and the addition of a quantity of x. The things like the top part where it was just 2x, the multiplication where it's not being added or subtracted to a value, those you can't assume are 0. It's only when you're subtracting a quantity or adding a quantity of x. And the reason why we're making that assumption is because we're saying that the x value we have is so tiny that when we go to round it for two significant figures, it's not going to look any different. Does that make sense? I hope. Right? Because all of our numbers are 2 sig figs. So our final answer should be rounded to 2 significant figures. So if we have 0.5 minus 0.02, by the time we rounded it to 2 significant figures, it would look like 0.5 again.
Yeah. I think you misunderstood my remind. There was like some calculation errors that you messed up on. That's what.
Oh, there was? Okay. I'll look at it because it's left over from last year. It's the one that I put up there. So there's a good possibility I missed one. So let's try another one and see if we can do this faster. So we got 15 minutes of time to work on this one. Do you remember specifically, Ami, which question it was from homework? Because we could go over and do that one too if you wanted. So I have the homework right here.
For the denominator part for 8C, there was a concentration of 1 mole of something of 2-liter flask, and you put down as 2 molarity, but it's like 0.5. I mean, so 1/2.
Okay. And that was question 8, you said?
8C, yeah. No, 8A. Never mind. 8A.
Okay. Yeah. Let me look. Yep. So 2 moles of pure NOCl in a 2-liter flask. Yeah, it should be 1 mole, not 2 moles there. What's crazy is it looks like I had that to begin with and then messed it up again. Because I can see my erasure And I can see where I had one.
You can see in the background.
Yep, because it's 2 moles and 2 liters, yeah. Okay, yep. So that should have been 1 mole. And I can actually see where I did it with 1 mole to begin with and then had changed the answer. So the mechanics is all the same. The X value is just going to be wrong because it'll be half the amount. Yeah. Okay, thanks, Ami. I'll try and fix that. Well, cool. Is that the only one you noticed?
Let me check. You can keep going with class. Let me see if there's something else.
Okay, yep. Okay. So PV-NERT can be used in the unit? Yes, that is, guys, anything from any previous unit can be used from here to the end of class. AP Chem, you cannot hit delete on anything. So everything is still fair game. Especially when we're talking about partial pressures, PV-NERT is absolutely a thing that's still in play. Okay, so let's go through this one, see how we can knock this out, and then the last 10 minutes so that we have a class. So it says write the equilibrium expression for Kp. We are given the balanced equation, so we didn't have to do that step first. So let's see. Annika, what would be my equilibrium expression for this guy?
K equals P sub H2 squared times P sub O2 over P sub H2O squared.
Perfect. So because this is a Kp, we're looking at the equilibrium for pressure, right? So it's asking us for Kp. That's where we use the rounded and we use the P sub. It's a very nitpicky thing on the part of the AP College Board, but that's what they want. Okay. So we have our equilibrium expression, and it says, suppose you start out with only water in your container, and its initial partial pressure is recorded to be 1.27 atm. What are the partial pressures of each species when the system reaches equilibrium? Okay. So we're going to just launch right into an ice table because it tells us that all we have in the beginning is reactants, which is the water. So if all we have are reactants to begin with, we're going to be shifting this way. So we know that we're going to be subtracting from the reactant side and adding to the product side. So we're going to fill this out. Okay. We have our balanced equation, 2H2O makes 2H2 plus O2. Okay. So we have to fill out our initial line. So what are we going to have initially? Olivia, what's going to go on my initial line to begin with? So Olivia, what's my I line for my ice table?
Sorry, were you talking to me? My cat jumped at me.
Yeah, I was talking to you. What's going to be on my I line here? Olivia.
All right. So you're gonna put 1.27 for 2H2O, and then 2H2 and O2 are just gonna be 0 because they're not there yet.
Good. And notice that we can use ATM. So you can either use molarity or you can use ATM, atmospheres of pressure, in our table. Good. So then we're going to have our change and our equilibrium. So we're going to need to fill those out. Pamela, what is going to be my change line for this one?
Two H2O.
So what's my change
And
line?
then 2 plus 1. So it'll be 2 moles.
So am I adding to this or subtracting?
Subtracting.
Yeah, I'm subtracting. And it's going to be, because of my coefficient of 2, subtracting 2x. So what is it going to be for the hydrogen? Subtracting or adding?
Adding 2.
Yep, 2x. And then what is it going to be for O?
1 addition.
Yep, so 1x. Okay, so we have minus 2x, adding 2x, and adding x. So then we have our equilibrium line. So Pamela, what would be my equilibrium line?
Would I have to subtract 1.27 from 2?
Yep, so we're gonna have 2x. So don't forget the x in there. So it's 1.27 minus 2x. And then 0 plus 2x is just 2x. And then 0 plus x is just x. Okay. So then, Pamela, what's the next step? Where am I going to put these numbers?
We're gonna have to get the
Where am I going to plug these numbers into?
in the equilibrium.
Yep. So I'm going to put those all into the equilibrium expression. So my Kp is going to be equal to 2x squared times x over the quantity 1.27 minus 2x squared. Okay. Now, it gives me I was like, where is it at? It's right up here. So my K value is 7.6 times 10 to the negative 16th. So the assume 0 rule is well in play, right? This is to the negative 6. Anything really smaller than negative 3, or actually negative 2, we can start assuming 0. So to the negative 16th, we can assume definitely that this x is going to be 0. What you need to do, though, is when you're doing this on the AP exam and you're assuming x is 0, you have to tell them that you're doing that, okay? And you have to tell them why. So assume x is 0 because k is small. Okay. So now this is just algebra class. We've left chemistry and now it's just straight algebra. So as we had before, 2x squared times x is going to be 4x cubed. That's going to go on top. So Kp is equal to 4x cubed over, we're going to assume that's 0, so that's going to become 1.27 squared. And that's going to equal my 7.6 times 10 to the negative 16th. So this is just going to require a little bit of algebra and a little bit of solving to get to my x value. So if you're somebody who really loves algebra and like solving for x, ice tables are for you. So 1.27 squared times 7.6 second e negative 16. So we're going to have 4x cubed equal to 1.22. Try and keep your numbers in the calculator if you can, times 10 to the negative 15th. Now we're going to divide both sides by 4. We're going to take the cube root of both sides. So we're going to take the cube root. The easiest way to do this is to raise something to the 1/3 power in terms of typing on the calculator. So parentheses, so the quantity 1.22 second e negative 15 divided by 4. And then I raise it to the 1 divided by 3. That's the same thing as taking a cube root if you raise it to the 1 divided by 3. And I hit enter. X comes out to be really tiny. So my x is equal to 6.73 times 10 to the negative 6. So we're going to come up with our equilibrium concentrations of everything. So I would say my concentration of H2, not concentration, partial pressure, my P sub H2O is equal to, not equal to, is approximately, so do the squiggles, okay, because it's not exactly 1.27 atm. My partial pressure of hydrogen gas is going to be approximately 2 times 6.73 times 10 to the negative 6. So take your number times 2. So it's approximately 1.3. So two significant figures there. 1.3 times 10 to the negative 5th ATM. And then oxygen is approximately the value of X, which is 1.3 times 10 to the negative, no, lies. What is that? 6.7. It's right down here. 6.7 times 10 to the negative 6 ATM. It's just your X value. Okay. Any questions on that? Honestly, the ICE table is really easy filling that out. The hardest part is remembering how to do algebra, because we sometimes forget that algebra exists outside of algebra class. So it's just the solving for X. Okay, so what I'd like you to do over the weekend is revisit your problem set 3, which is ICE tables. So if you didn't do that yet, or you couldn't finish it all because you were still kind of confused on how these work, make sure that you're doing that. Ami, I will fix that error on the answer key. It'll just be a minute because I'll have to rescan it and put it back in. But yeah, I can fix that for sure.
Also, I figured out in 8C, I think
8C?
you switch, you switch the positions of CL2 and I think NOCL.
Okay, cool. Thanks for bringing that one up. So basically, I should just do number 8 over again. So I can do
No,
that.
8B is all right. I think that's good.
Yeah.
Just
Okay. Thanks for
Yeah,
finding it for me, Ami. I appreciate it. Let me see again. What did we do?
Hey, miss, don't forget to stop recording.
Oh, thank you for reminding me of that. Thanks. All right, guys. Yeah, so Ami, I'll get those fixed and put those up there. If you find anything else, let me know.
I think that's all. All right, see you, miss.
Yep, see ya. Thanks.